Good evening. My name is Patrick Ryle. I'm your host this evening for Science and Nature. Our guest today is Dr. Allyn Clarke, who is the head of Ocean Circulation Division in the Department of Fisheries and Oceans at the Bedford Institute. Dr. Clarke is here this evening to talk about the coming document from the Intergovernmental Panel on Climate Change. Going to give us some idea about how a group of scientists, how a panel like this comes to a consensus, and perhaps talk a little bit about what their main conclusions are for the future and the suggestions that they have as to what we should do. Dr. Clarke, first of all, could you tell us what the IPCC is and how it functions?
The IPCC was a organization which was set up following the Rio Summit for the Environment. It was set up by the United Nations, and it's an intergovernmental panel, which means that the nations of the world have the responsibility and the right to appoint various scientists to this organization. Its purpose is to provide the United Nations and the nations with assessments of the state of the issue of climate change associated with the world. And they do these assessments every 5 years. The first assessment was in 1990, and we have just completed the second major assessment, which was in 1995. However, we didn't really complete it until a meeting in the end of January 1996.
So that's the document which is being released now, is that right?
This is the document which was approved at a meeting at the end of January of 1996, and the document as a whole should be published by Cambridge University Press probably within the next few months. This is a very valuable document because it attempts in one document to summarize what the global community of scientists think of the science of climate change, the possible impacts that climate change might have on the world, and the types of measures which are available to nations and governments to mitigate those impacts which climate change might bring.
Since this is an intergovernmental panel, and you said that nations have the right to appoint people to this, is this a truly scientific panel, or is it hostage, as so many intergovernmental things are, to different countries' politics and views on the world?
Because there's so many nations, and because most nations who are strongly involved in the climate agenda in the research have strong science components, it's difficult for nations to subvert the process. If a scientist is appointed to these panels and doesn't have the prestige or the background in order to defend their point of view on the panel meetings, then ultimately that it's going to be unsuccessful for the nation to attempt to pack a panel with people who are expressing political views rather than scientific views. Of course, at the end of the process in Madrid, one aspect of the panel's final document was quite controversial. That is, the question of whether or not science can say whether or not the climate change which we see now can be attributable to human activities. Two nations, in fact, ultimately refused to go along with the consensus, and they were noted in the final report of having abstained from this consensus. So it is interesting, though, in that even when they came to publish the final proofs to Cambridge, both these nations wanted that footnote removed. So they don't want to be seen in a public document like this of having gone against the majority.
So it's not a process there whereas the whole thing can be held hostage by political purposes. With a bit of discussion, a scientific consensus will come out, and when we see that, we can have a good deal of confidence then in that document.
Well, the panels operate on the rules that everything has to be written and reviewed and based on the primary refereed literature. So you can only argue on the basis of primary publications. So basically this document rests on the normal peer review system of science. So it is, unless you can find a lot of published information that goes for your minority view, you don't have much chance in putting forward that minority view. So you have to have your opinions based by really good science.
This is the second of these publications. You said the first one is 1990. Have there been significant differences or evolution of thought between one and the other?
Not really, and that's one of the frustrations of the scientific community. The political community insists that we do these assessments every 5 years. It takes about 2 years to do an assessment, which means that we are actually thinking for to the year 2000 assessment will start in 1998. Well, this is large-scale science, which we're trying to assess. Large-scale science takes, especially observational science, takes several years to plan. It takes several years to do. You eventually write up your papers. Most papers spend a year in the review process before they hit the press. So a 5-year time scale is a very short time scale when it comes to the science. The result is it was harder to find scientists who were willing to spend the effort in 1995 to do this review than it was in 1990, and there's some fear that it's going to be even harder in the year 2000 because people don't see this as a new and exciting thing to do.
So I mean, with this, their contributions to that, you're suggesting might not be viewed by their colleagues as a really productive use of their time, as opposed to advancing their own science. Is that the feeling that some people have?
I think it's the feeling, not just that by your colleagues, by yourself. If, as a scientist, I'm willing to do spend some effort doing a major review paper if by doing that major review paper I think I'm advancing the understanding of a large body of science. If I know that there's another review paper that's only 3 or 4 years old, I'm not willing to spend 2 or 3 months of my time reviewing something which has already been reviewed to get a small incremental increase. And I think it's more people looking at their own personal time and their own personal interests. So there is a negotiation between the scientific community and the political community to try to say maybe these assessments, the major reassessment should be every 10 years, with special minor reassessments in between for those points where there's been some major development.
Would you like to tell us a little bit about what the major conclusions are coming out of this report?
Yeah, I think I'll concentrate on Working Group 1. The IPCC is divided into 3 working groups. The first one is the science of climate change. And as a climate scientist, that's where I'm most comfortable with. If I were a biologist or an agricultural person, I'd probably be more comfortable with the second working group, which is the impacts of climate change. And if I were an economist or a politician, then I'd be more interested in the third working group, which is what sort of mitigation efforts can be done. I've summarized the major points on a series of slides. So maybe if we go to the first slide, The first issue which Working Group 1 deals with is that of the greenhouse gas concentrations. And their conclusion is that the greenhouse gas concentrations have continued to increase. What is the largest greenhouse gases in terms of their effect are carbon dioxide, methane, and nitrous oxide. And these have increased significantly since 1750 by 30% and 145% and 15%. These are really very striking increases. The working group assessed that these increases are largely due to human activities. We know that looking in ice cores and things, we know that carbon dioxide does change over geological timescales, but over these timescales we feel that those changes are due to fossil fuel use, land use changes, and agricultural practices.
How do those concentrations compare to concentrations in the recent geological record? Are these higher than we've seen in sort of the time that mankind has been on the Earth?
Yes, they are higher than when mankind's been on the Earth, but they're not the 30% increase in carbon dioxide. I think if you look at during ice ages, carbon dioxide contents were more than 30% less than their present values. So the swings aren't outside of the range of the swings, but I don't think in the ice records we've seen levels this high in the sort of last 100,000 years. If you run radiation models, then you find that the direct radiative forcing due to these measured increased concentrations should be about 2.5 watts per meter squared in radiation forcing. That's actually quite a small number. On a warm summer day, we're receiving radiation at these latitudes in summertime of several hundreds watts per meter squared.
So this is a change of less than a percent.
This is a small change, and that's just given as an illustration of why it's so difficult to detect the effects of these changes. These are small changes. But these are also the same size changes as if you work out the radiation changes that are due to the orbital changes, which are thought to be the cause of ice ages. You find that those orbital changes result in solar radiation changes to the Earth of this same 2 or 3 watts per meter squared. It also may be about the same order of magnitude as the changes in the solar output due to sunspot cycles. Recent satellite measurements show that the solar constant changes over times of about 15 years with changes about this same order of magnitude. So there's lots of things in the climate system which change at this size.
There's some difference, though, isn't there, in the distribution of that radiation as to whether it's due to Milankovitch cycles or whether it's due to sunspot activity, and that one would be more uniformly distributed about the Earth than the other?
Oh yeah, there's many differences on how the radiation forcing is distributed. So an orbital change does major changes in how much radiation comes in summer as opposed to winter. And this change, which is a change in the long wave radiation, is a redistribution of where the Earth radiates its energy back out to space. So it's a different process. The final major conclusion on this was that if we continue to do our CO2 emissions at this rate, we would double our CO2 by the end of the 21st century. So we double our concentrations. And that's taking us well beyond anything which we think that the Earth has seen in geological time.
The obvious question that comes from that is, what is the consequence of those?
Yeah, and that's, well, first of all, that's in some ways, that's the warming side of the equation. The difference between 1990 and 1995 is that climate scientists started looking at the aerosols in the equation. Now, the aerosols are the small particles which are put into the air by burning fossil fuels mostly, and car exhaust. And we found that the assessment says that the net cooling globally of all the aerosols that we put into the atmosphere, or continue to put into the atmosphere, is about a half a watt per meter squared. However, locally, this aerosol forcing is the same order of the global the warming potential of the gases. So it's 2 to 3 watts per meter squared. This means that in the northern hemisphere, where we have most of the industrialization, you have a lot more aerosols in the atmosphere, and therefore we're counterbalancing the global warming potential. And that is used to account for the fact that over Western Europe and North America, we haven't seen as much warming as we've seen over other parts of the globe. The panel points out that these aerosols are quite short-lived because they're only in the troposphere, they're only in the lower atmosphere, and they rain out fairly quickly, while gases like carbon dioxide and methane spend hundreds of years in the atmosphere.
There's another drawback to these aerosols, isn't there? Because you're looking largely at sulfates and therefore cause of acid rain.
That's right, but then there's recent papers that say that the acid rains have increased productivity of certain of the northern vegetation because the acidity of the rain releases more nutrients from the soils, and as you decrease the acid rain, then you actually have to increase the fertilization of your soils. So there's
even that's got a small advantage somewhere.
The one thing you learn when you start looking at climate change and global change is the system is hugely interconnected, and that for every bad thing or negative thing which happens, there's often little positive feedbacks which come into the system. So what does this gas concentration do? Well, first of all, the panel then looks at what does climate look like now as opposed to what it looked like 100 years ago. And the conclusion is we're warmer. We're not very much warmer, about a half a degree warmer, but we are warmer than we were at the end of the 19th century. More interestingly, the nighttime temperatures are warmer, have increased more than the daytime temperatures. And that's indicative of changing the long-wave radiation. You know that if if the night's cloudy, then it's going to be a warm night. If the night's clear, then it's cold night. And the reason why it's warmer on a cloudy night is the radiation from the Earth goes up, hits the clouds, and bounces back. And so the Earth doesn't cool as much. So this conclusion is consistent with changes in the greenhouse gases trapping more of that long-wave radiation. Also, the global sea level has risen between 10 and 25 centimeters in the past century. So those are the observations which globally one can make. So if we look at the next slide, this is the controversial conclusion of the Working Group 1. The balance of evidence suggests a discernible human influence on global climate. The actual conclusion has a few more caveats written on it. You can imagine scientists,
especially intergovernmental.
Intergovernmental scientists want lots of caveats in there, and good science wants caveats in there. But basically, this is an important conclusion compared to 1990, where the conclusion in 1990 said that the present warming was not inconsistent with the predictions.
Mm-hmm.
This is actually saying something more.
So more confident now that the warming
more
is
confident.
anthropogenically caused rather than just
some part of it is.
Right.
And although there's caveats, but it's based on the pattern of the climate, of the temperature change. And it's based on its vertical structure as well as its day-night time difference and its geographical distribution.
Is there also a seasonal difference? I mean, could it be that winters are getting a bit warmer? Or?
Yeah, the winter and summer differences are there too, but on this particular pattern change which they did, they didn't do that pattern change. Climate model, the whole science of climate modeling is recent and in its infancy, and a lot of the climate models actually don't do the seasonal cycle very well, and a lot of them actually don't do the diurnal cycle, the day-night cycles very well. So it's a little hard to do some of these things. The real caveat is a real admission that this detection is very difficult given the wide range of natural variability within the climate system. When they did the pattern recognition, on climate models that are forced by the greenhouse gases and the aerosols, but climate models which don't have the natural variability in them. So there's some controversy in some of this detection work because they haven't accounted for the variability. Some of the parts of the variability looks very much like some of the parts of the aerosol signal. For example, the North Atlantic being very cold right now is part of a natural variability which is known as a North Atlantic cycle. Well, that pattern looks suspiciously like the same pattern you would predict from aerosol distributions from eastern United States, central Canada,
hard to separate,
and western Europe. So it's hard to separate.
Right. You mentioned the greenhouse gases and the aerosols. Are these models now, are they taking into account effects of the ocean and cloud cover? Or?
Well, the models for this assessment take into account the ocean and the clouds better than the 1990, but still not to a level which I, as an oceanographer, am happy with, and certainly not to a level which cloud physicists are happy with. But we're using coupled ocean-atmosphere models. The assessment has to say what we expect, because that's what the politicians want us to say. One of the real problems in all this assessment process is trying to understand what the global economy is going to do. So the IPCC has a whole bunch of different scenarios, and depending on whether or not business as usual, we keep on burning fossil fuels and develop all the brown coals in China and things like that, or moderate rollbacks or really intense rollbacks. So this is a mid-range emission scenario, best estimate type calculation which they've done, and this says that we think that the raise in global mean air temperature in a century will be about 2 degrees globally, and that value is about 66% of the value which one gave in 1990. So we're
the estimates are a little bit lower.
We're continuing to decrease the estimates. So the critics who say, that the climate community started out large and is slowly heading towards zero, I mean, may take some comfort by this, but the difference is because they've included the aerosols, and they've made some improvements in how they treat the carbon cycle. And this would also say that for that temperature change, the sea level rise would be another 50 centimeters, which is half a meter.
So would this get us back to the same similar temperature and sea levels as there were in the medieval warm period at the time when the Vikings were sailing across the Atlantic?
No, actually, we think that we're pretty close to the medieval warm period right now. So, although the ice conditions recently in the North Atlantic have been pretty rough, so in the North Atlantic zone of influence. We haven't been in the medieval warm period. We've been more like the, if you lived around Iceland or in the Labrador Sea, in some winters you might think you're more in the Little Ice Age, but globally I think we're close to the medieval warm period. Maybe half a degree more will get us to those maximums. The final part of Working Group 1 is report is just pointing out that this is an interim assessment, like all scientific work, admitting where the weaknesses are, and saying that we have to improve the climate models, especially in the feedbacks associated with clouds, oceans, sea ice, and vegetation. Those are important climate feedbacks, and none of them are very well modeled in the models, mostly because in order to model any one of those requires as much computer resources as the rest of the climate model by itself. So it's still a question of computer resources.
So we can expect perhaps the models to improve over time just with the increases in computer power that's available for the modeling?
That's the hope.
That's the hope.
That's always the hope.
If you could just choose a few little statements to sum up the major conclusions of this and the prognosis for the future, does this report propose any major economic changes? You mentioned the business as usual scenario and other scaling backs, but on days like yesterday, some of us might have thought that global warming would be a good thing, and I mean, should we be looking at great costs in order to maintain this present temperatures?
These reports don't make those recommendations. The purpose of these reports are to give the policymakers, the politicians, with the basic information which they can then use to make those recommendations. So these reports are, if you do this, these are scenarios. If you do
this is laying out various possibilities.
This will be the consequence.
All right. Well, I think this is very good to see this latest report coming out in the near future from the IPCC, and hope that our politicians will be able to look at this and see what the scenarios are and bring them to the people so that we can make our contributions to the decisions as to what has to happen to keep this world livable for us and our children in the future. Thank you very much, Dr. Clarke.
Thank you.